In a number of important cases, a complete integral of the Hamilton-Jacobi equation can be found by a method called separating the variables. Suppose some coordinate, say the first, and the derivative of the action with respect to it appear only in one particular combination, and that this combination involves no other coordinate, no time, and no other derivative. Then we look for a solution as a sum of two pieces, one depending on that coordinate alone, and one carrying all the remaining variables and the time. Substituting this into the equation, it must hold identically for every value of that coordinate. But when the coordinate changes, only the combination changes, so the combination must be a constant. So the single equation splits into two. The first says the combination equals an arbitrary constant. It is an ordinary differential equation, and simple integration gives that part of the action. The second is still a partial differential equation, but with one independent variable fewer. Separating one variable after another this way reduces the search for a complete integral to a chain of one-dimensional integrals, which is to say to quadratures. For a conservative system, only the s-coordinates have to be separated in practice. Once the separation is complete, the integral is the sum of one term per coordinate, minus the energy times the time. A cyclic coordinate is the simplest special case. It does not appear in the Hamiltonian at all. The combination reduces to the derivative of the action alone, and that term is just a constant times the coordinate, the constant being the conserved momentum belonging to it. The term with minus the energy times the time, in a conservative system, is exactly what comes of separating the time as a cyclic variable of its own. So every earlier simplification made with cyclic coordinates is contained in this method, and to those are added cases that separate without being cyclic at all, such as spherical or parabolic coordinates. This makes Hamilton-Jacobi the most powerful route to the general integral.